area under the graph of f of x, of course on the interval 0, 2, using 2, 4, whatever sub-intervals. And illustrate with leftmost point, 2, rightmost point, 3, midpoint. What's all this? Much easier than you think. So first I'm going to graph the function, and then I'm going to divide the interval into 2 and then 4 and then so on and so forth, subintervals of equal width. So let's take it slowly. As you know, the first problem, it will take me like forever, and the second one will take me 5 minutes. But the first one I have a lot to tell you about. So here's the graph. 1, 2. And 2 squared is 4, 4 plus 2 is 6. So 1, 2, 3, 4, 5, 6. So then at 0 is 2, and at 2 is 6. So here's the graph. It's quadratic. The interval is 0 to 2. And I'm interested in determining the area. What area? I don't want to just shade it in. It's this area. This is what I want to determine. The area under the graph of x squared plus 2 between the x-axis and the graph of the function. First, I'm asked to find the area using 2 subintervals. Okay then. So the area left 2, using the leftmost point. I'm going to, my only chance here is, well, there is another way, it's called the trapezoid rule, but for now, we're using rectangles. So on this subinterval, I'm going to, because I have 2 already, so on this subinterval, I'm going to approximate this area using a rectangle that has the height, the leftmost point of the interval, where the function starts actually here. So this is one area with a leftmost point. For this piece, using the leftmost point, I will have this area. Okay, so let's determine it. The area approximated with 2 subintervals using the leftmost point will be base 1 times height, f of 0, plus base 1 times height, f of 1. F of 0 is 2. F of 1 times 1 is still 2. F of 1 will be 3 times 1 is 3. So here's the approximation. This is the approximate area under the graph of f of x using the leftmost point with 2 subintervals. Okay, so now let's repeat for a right tip. Same graph. So since you understand what I'm trying to do here, I'm not going to graph a lot of details. And now with the rightmost point, I have this rectangle. With the rightmost point is the height. Base times height. Now base times height. And then AR2 will be base 1 times height f of 1 plus base times height f of 2. Well, f of 1 is 3 times 1 is 3 plus f of 2 is 4 plus 2 is 6 times 1. So this is 9. Question for you. In the first situation we got 5. In the second situation we got 9. Yes, you're going to say, and I agree, they are nowhere near the exact area. I agree, this is an approximation. Which of these two for this particular function is an overestimate and which one is an underestimate of the correct exact area, which I don't have?
Nine is an overestimation.
Of course. And the other one is an underestimation.
5 is under.
Of course. We agree so far. Yes?
Yes.
Perfect. Now let's look at what happens with the midpoint. So with the midpoint, again, I'm not going to graph too many details like I did with the first one. Here it is. Here's our graph. This is 0, this is 1, this is 2. Now, here is my midpoint, which is 0.5, and here's my midpoint, which is 1.5. I will draw the height for that point, and I will create for that height a rectangle. For that height, where it meets the graph of the function, I will create another rectangle. And now this will be the area with M2, the midpoint. And that AM2 will be base 1 times height, f of 0.5, plus base 1 times f of 1.5. I will put it in my calculator. So in y equals, clear everything, and put in x squared plus 2. And then second and table, I'm going to plug in 0.5, and I'm going to plug in 1.5, and I'm going to add them up, and I get 6.5. Which of these is the best approximation? Which of these three options is
6.5?
Of course. 6.5 with the midpoint is the best approximation, of course. Perfect. Great job. Now, here's my next question for you. When we started the problem, we said 2 subintervals of equal width. Then we said 4. And then we can continue with 8, with 16, with 32. Which of these will you think will be the best? And which one will give us the exact? How many will please you? How many subintervals you will say, oh, I'm happy with this and I know it's going to be the exact area? How many subintervals will please you?
None of them will give you an exact value.
Excellent. So then, how many subintervals will fill up the entire area?
Infinite amount.
Right. What kind of concept is this? When we look at something that happens at infinity from the previous chapters, which concept?
Indeterminate?
There is a concept, an operator. What operator took us to infinity? Many times. It's called the One operator sometimes took us, not always, but sometimes took us to infinity.
I mean, the pattern that's I'm seeing right now is just multiplying by 2.
What operator took us to infinity?
The limit.
Thank you. This is the concept of the limit. So the number of subintervals is denoted by lowercase n. So then the exact area will be definitely a limit. Definitely when n, as we established, approaches infinity. But now we have to identify what to write here. Of what? So let's look back. I know we only did it with 2 subintervals, but what did we do here? What is this? Base times height plus base times height plus base times height plus base times height.
Summation.
Thank you very much. From the very first interval to the last one, and the last one will go to infinity. And now let's establish this must be a product of 2 things. Base times height, base times height, base times height. Let's see how we write the base. The notation for the base is delta x. So delta x is the base of the rectangle in our situation. And then we are multiplying by a value of the function, right? So base was the same all the time. 1, 1, 1, 1, 1, 1 for all subintervals. This is the same. So this is calculated as, of course, as b minus a over n, where b minus a is the interval, a comma b. In our case, it was 2 minus 0. 2 minus 0, 0 comma 2. But now let's establish this piece. In the first position, it was f of 0.5. In the second position, it was f of 1.5. In the third position will be 2.5, f of 2.5. In the next position will be f of 3.5. In the next, f of 4.5. It will depend on I, depending on which subinterval we find ourselves. So this will be x with I. And this is this Riemann sum. This is called the Riemann sum. So the exact area under the graph is the limit of the Riemann sum. The exact area under the graph will always be the limit of the Riemann sum. Okay. Before I show you the technique of finding the exact area, and we're going to start with this function that we are trying to determine the area under the graph of the x squared plus 2 between 0 and 2. I'm going to say something that I really don't like saying in general. We need to memorize. I don't like that. I prefer explaining, understanding, and then it will stay. But memorizing just numbers or an expression is not something I like to do, but we have to do it now, and I can prove any of those if you'd like. We can prove what I'm going to show. So these are 4 identities. They can be proven using mathematical induction. So there are 4 identities that we have to memorize. Sorry. The first one is quite easy. The sum from I equals 1 through n from 1. This is no problem. When I is 1, when I is 2, when I is 3, dot, 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 exactly 3 dots plus 1. N times. What will that equal to?
Sorry, I times n.
Uh,
Sorry,
just-
one times n.
Exactly. Perfect. So that is easy to remember. Now number 2 is the sum from I equals 1 through n from 1 from I. Sorry. I rushed. From I. No minus, no plus, nothing. Just I. Sorry. From I is 1 plus 2 plus 3 plus dot, dot, dot plus n. We're not going to write it like this. It's n plus 1 divided by 2. The third one, the sum of I equals 1 through n from I squared. 1 squared plus 2 squared plus 3 squared plus dot, dot, dot plus n squared is, this is the most difficult one to remember, n plus 1, 2n plus 1 divided by 6. The last one is not difficult. It's the sum of I cubed, which is 1 cubed, 2 cubed, 3 cubed plus dot, dot, dot plus n cubed, which is identical with this, but everything squared. So here's a note. The limit of the Riemann sum, which is the area under the graph, can be determined only for linear, quadratic, and cubic functions. If you ask me, find the limit of the Riemann sum for f of x equals sine x, I'll say sorry. I can't. Because I only have these 4 identities to work with. So, nothing else. And now, after we determine the exact area under x squared plus 2 between 0 and 2, we will choose any other problem you'd like. But it has to be linear, quadratic, or cubic. So coming back to our problem, which was f of x equals x squared plus 2, and the given interval was nice one. It started at 0. Let me stop the next